Now we start getting into some chemistry. Video 3-1, Foundations of Atomic Theory, Development of Atomic Models, and Forces in the Nucleus. So, Chapter 3, we are looking at the atoms, building blocks of matter. So, first thing, Foundations of Atomic Theory. Several basic laws introduced after 1790s. Emphasis after the 1790s was now on quantitative analysis. Prior to that, people who had been studying science were making more qualitative observations rather than quantitative analyses. Now, once they started actually measuring quantities, a couple basic laws showed up. One of them was the law of conservation of mass. Mass is neither created nor destroyed during ordinary chemical or physical processes. And again, don't forget, chemical and physical processes. Okay, next, we have the law of definite proportions. Chemical compounds contain the same elements in exactly the same proportions by mass, regardless of the size of the sample. Because a compound is a pure substance, every particle is made up of exactly the same chemical composition. So, for example, sodium chloride. Every single sodium chloride unit has one sodium, one chlorine atom. So, as a result, by mass, it's always going to be 39.34% sodium and 60.66% chlorine. Okay, now, they also came up with the law of multiple proportions, which just simply says if two or more different compounds are composed of the same two elements, the ratio of the mass of the second element combined with a certain mass of the first element is always the ratio of small whole numbers. Simple, right? Okay, now what does this actually mean? Okay, well, first of all, let's look at this. In order for this law to apply, you have to have two or more different compounds with the same two elements. So let's look at an example. If we have two compounds that have the same two elements, CNO and carbon monoxide, and CNO and CO2. Okay. So for the same mass of carbon, the mass of oxygen in CO to the mass of the oxygens in CO2 will be in a 1:2 ratio. Okay. In other words, they're saying the O to O ratio is going to be 1:2. And you say, oh, well, that's pretty obvious because there's only one oxygen here and two oxygens there. Okay. Now, in terms of mass, okay, if you took 28 grams of CO and 48 grams of CO2, okay, why are there different masses of CO and CO2? Because we have to have the same mass of carbon. Both of these will contain 12 grams of carbon. So you have 12 grams here and 12 grams there. Okay. Now I can compare the masses of oxygen and oxygen. The CO would have 16 grams and the CO2 would have 32 grams. Okay. So, before we can compare oxygen to oxygen, the carbons have to be the same mass, 12 and 12. Okay. Then the ratio of the oxygens will be 16 to 32, or a 1:2 ratio. Okay. Now, next question. What about the carbon to carbon ratio? Okay. Are both of these going to be 1:1? Okay. Problem is, we can't compare the carbon to carbon and say it's 1:1 because if you want to compare the carbons to each other, the oxygen ratio must be the same, 1:1. Right now it's not. So, what if I took twice as much CO2? This would be twice as much, this would be 24, this would be twice as much also, 32. Now you can compare the oxygen to the oxygen. Okay. So in this case, O and O will be 1:1, but now the carbon will be 24, which came from here, and this carbon will still be 12, which came from there. So the ratio of the carbon to carbon is not 1:1, it's actually 2:1. Next thing, development of atomic models. Okay. Prior to 1790s, people had been thinking about atoms and things like that, But the first person to actually come up with a comprehensive atomic model, in other words, what they thought an atom looked like, was John Dalton in 1808. And he came up with 4 basic ideas. Okay. His first one: all matter is composed of these extremely small particles called atoms, and he said they can't be subdivided, created, nor destroyed. Okay. Atoms of the same element are identical. Atoms of different elements are going to be different from each other. Atoms combine in simple whole number ratios to form compounds. And in chemical reactions, the atoms will either combine, or they could be separated, or be rearranged somehow. Okay, now, which of these were later proven wrong, and why were they wrong? Okay, well, turns out that the ones that atoms could not be subdivided. Atoms can be subdivided. Okay, and you know atoms are not just the smallest particles, they are made up of protons, neutrons, electrons. Okay, and the second part that was wrong was atoms of the same element do not have to be identical to each other. Okay, so how did those postulates of Dalton's model get disproved? Well, people had to go and discover some things. So in 1897, a guy named J.J. Thomson and also Robert Millikan in 1909, their work helped to show that atoms were made up of smaller particles. Okay. And Thomson used cathode rays to determine that atoms contain small negatively charged particles called electrons. Now, these electrons had to be coming from the atoms, okay? Which meant that the atom had to have smaller particles. And since they knew atoms were neutral, atoms, because they knew electrons were negatively charged, there must also have a positive charge to them to balance out the negative part. Okay, so what's a cathode ray? Well, this is what's known as a cathode ray tube. Okay, visible cathode rays were basically made up of electrons, and they knew that these particles could be deflected by a magnetic field. So these had to be particles and not just like light. Okay, and the only place that these particles could be coming from were atoms. Okay. Other particles had to account for most of the mass of the atom, though, because they helped. Millikan helped determine the size of the atom in an experiment known as the oil drop experiment. Okay, this one isn't in your book, but if you're interested, you can go look it up. Pretty easy to find and figure out what he actually did. But this basically helped figure out the size of the charge on the electrons, and as a result, also the size of the electrons themselves. Okay, next thing, Rutherford came along in 1911. Okay, what was the structure of the atom? You knew they had negative parts and positive parts to it. Okay, well, his experiment was the famous gold foil experiment. Okay. Thomson assumed that the mass and the charged particles were evenly distributed throughout the atom. This is kind of known as a plum pudding model. Okay. So basically, this sphere, kind of like pudding, had a positive charge to it. The electrons were kind of like the plums, and they all had negative charges in them. You had enough of the electrons to balance out the positive charges. Okay, so Thomson figured, well, if you shot some particles at the atom right here, okay, most of the particles would pass through the atom, pass through the gold foil, with only, at the most, a slight deflection. Okay, so what happened? Most of the particles did go straight through, but some of them showed a little bit deflection, and some of them showed a wide angle of deflection, okay, as they passed through. In other words, instead of going straight through, they were shot off to the sides. Some of them almost came backwards. Okay, so this was his experiment. He set up something that was called an alpha particle emitter. This is a radioactive particle, and shot it through a little screen. This screen was set up for detection, basically. When something hit it, you'd see a little flash here or a flash here. And he said, well, most of the particles should just go straight through, and most of the flashes would be here, which is what he saw. He said, well, maybe a couple of them would be here and here, which is what he saw. But these over here, he didn't expect to see. Okay. the plum pudding model wasn't going to be able to explain this. And the ones that came back and hit the screen back here, those are really weird. So what he figured out then was that there must be something called the nucleus. Okay? The nucleus must be small because most of the particles went straight through without being deflected. They had to be dense, and they held a positive charge. Okay? So the rest of the atom was pretty much just empty space. The number of electrons in the nucleus determines the atom's identity. Sorry, number of protons in the nucleus determines the atom's identity. Okay, so Rutherford basically said, well, the atom is probably kind of going to look like the solar system, okay, where the sun's in the middle, the electrons are going to be your planets orbiting, okay, and the sun is basically the nucleus. This is where your positive charge was. Okay, now, forces in the nucleus. Okay, repulsive forces should exist between protons in the nucleus because, like charges, the protons have to be have positive charges to them, so they should repel. So, how are protons stuck together with other protons? How come we can have atoms that have more than one proton in the nucleus? Shouldn't they, if they come close together, shouldn't they just be repelled apart? Okay. In other words, why doesn't the nucleus just fly apart? Due to these repulsive electromagnetic forces. The force that exists between positive charges and negative charges, or positive and positive charges, these are known as electromagnetic forces. Okay. Well, turns out there is a force known as a strong force, okay, or this is called the strong nuclear force. And basically, it's the attractive force that acts over very small distances in the nucleus. Okay. This causes the protons to stick to other protons, also the protons to stick to neutrons, and neutrons to stick to neutrons. But again, it can only act over very tiny distances. Okay. Now, gravity. Gravity should exist everywhere. Whenever you have anything with mass, there should be a gravitational force. Okay? So gravity is present in the nucleus, but it's a negligible force. Okay? Why? Well, the size of the gravitational force has to do with the size of the mass. And what do you know about the sizes of protons and neutrons? So the review question. How many parts of Dalton's original atomic theory were proven wrong? So 1, 2, 3, all of them, or none of them?